Okay, so let me go back a step or two from my last talk, because I have a feeling I was a little bit out of focus at some point here. So we are going now to consider a condition for existence of map which realize the norm cost, the cost x minus y, absolute value. And we know there exists a Kantorovich potential U, which is Lipschitz 1. So, so we look at all points for which we are given this U. We are looking for all points x, y in the space such that this equality holds. And the first obvious observation is that if there are two such points, x and y, such that ux, uy minus ux equal x minus y, then it's obvious, almost obvious, that all points in between also satisfy this equality. So suppose this point x1, this is a y1, say. So of course, x1 minus x plus y1 minus x1 plus y minus y1, because they are all on the line, this is equal to y minus x on the one hand, and 1 minus x equal, like we assume, uy minus ux. On the other hand, because this function u is Lipschitz 1, it has a constant Lipschitz less than 1, these are bigger or equal to u x1 minus ux plus uy1 minus uy plus uy1 ux1 minus ux, uy1 minus uy, and this equal to uy uy will be plus minus. This equals again to uy minus ux. So you have equality all the way. If you have equality all the way, of course, this is true for any 2 points on the line. So we define this line as a part of transport ray, and we know that each point on this line will shifted by the transport to another point on this line. So we can extend this segment to its maximal possible way, and we have a bunch. We get a bunch of segments in the space, in the space omega cross omega. What we proved is that on each point on this line, on the interior of such maximal line, U is differentiable, and its gradient is at each point in the interior of this segment, the gradient is fixed, which is the unit direction of the segment. So the trick we are going to use now is we want to get rid of all non-monotone planes, because we know there is not uniqueness in the metric case. So we define this funny cost called CA. This is a set A of all points which satisfy the inequality, and CA is a function which is infinity, which is the quadratic cost between xy, and if xy is in set A, and infinity otherwise. So it's our semi-continuous, and we minimize over this set. We minimize the Kantorovich potential over this set. Obviously, any minimizer is a transport map, right? For the W1, because any measure which is supported in this set, we know it's optimal. So we hope to see that there is only one for all possible measures supported on this set, which has a marginals mu and nu. There is only one which minimizes this cost. And this is the one we are looking for. And we hope to prove that this is given by on a graph of a mapping. So that's what I said. The optimal transport is also optimal for W1. And another observation that we know that any optimal transport of CA is cyclically monotone with respect to CA. Okay, remember what does it mean to be cyclically monotone? It means that for any chain, if we make a cyclic permutation or any permutation of this chain, we get we do not get below. We do not get something smaller, just maybe some higher value. So if this is quadratic, so let's look at the chain of just two pairs, x1, y1, and x2, y2. So we know that y1 minus x1 square plus y2 minus x2 square by cyclic monotonicity, this is smaller or equal than x1 minus y2 square plus x2 minus y1. So this is just cyclic monotonicity in the case of pairs, or cycle of two. But if you open the brackets, what we get is just, excuse me, what we get is, did I jump? Going backward. No? Yeah. Okay. Here. So this cyclic monotonicity gives us actually this inequality, which means that y1 minus y2 times x2 minus x1 is non-negative from this. It just means that there's a monotone map. Well, like we saw in the one-dimensional case. Only in this case, we do not build it from the accumulation function of some measure, because the measure is not defined on a line. The measure is defined on the whole space. We are only looking on the line. We don't know how to define a measure on it, but we know that the optimal transport is supported on the line, and it is monotone in this sense. So it take so the image of this point, if this is the image of this point, then any other point, the image of any other point will fall before the image of the higher point. Okay, so this actually like a monotone function on a line. So we know that a monotone function may have just counter is always a monotone plan or monotone transport plan is always on a graph of a function which is a single valued except at the points of the jump. So you may have monotone function at most countably many points of jumps. And so we want to, so this is the bed set, the point, because on the point of the jump, we don't have a single value the map, and the map can be anything on the gap between the. So we want to see that all these bad points are of Lebesgue measure 0. Right? That's what we hope to do. So, so we look at the space and we break it to subsets which is related to the line, to the transport line, which we call trans. This is a set of transport line. So, so we have several types of points. If a point xy is in the support of the optimal gamma, then either x is a singular point of the function mu. Singular means non-differentiable. So we don't care about it because we know by Rademacher theorem that Lifshitz function has only 0 measure of non-differential point. Another thing may be that x is a point which is not in any transport line because it's isolated. It has the Lifshitz constant at the point x is 1, but there's no line which there's no line like this which goes through this point. Yeah, so the line actually, maybe the line shrink to just 1 point. This is like a dust. So these are bad points, but in fact, it was later, years after the first proof of Sudokov, it was Ambrosio who proved actually, I'm not sure, Ambrosio or, no, I think it was Gangbo and McCann proved the claim that this is actually a null set because U is C concave. And for C concave sets, there are no such points. So any point which has Lifshitz constant 1 is sitting on a line of some size. So this set is really empty. The other set is all points which are at the end point of the transport line. This is trans plus means the point which is in the end of the maximal interval. So in this case, x equal y also, because you know y is always bigger than x. So if you're at the end of the interval, it maps to itself. And the other points are the points on the, like I said, the points on the interval itself, which is which are not singular and not at the end point, but may have a jump in the monotone map of the line. So the original proof by Sudokov in '76, he realized that that the transport plane is actually is composed of transport on the transport line, and he and the gap in his proof is that he did not really prove his argument for to show that the set of bad points are of measure 0. I will we'll see what is the best. It's a very delicate point, but here we define all the point on the line, excluding the endpoint, which has such that the number of jump points is bigger than 1. So call this set B. The set B is the union of all transport line on which carry more than one jump point, including, and of course we have to prove that all the endpoint of this curves is also set of measure 0. This is also done later by Ambrosio. Okay, so this is the set B, the bed set B. That's what I call B. We know that there exists very bad, very strange, subtle better example. For example, you may have uncuttable set of this joint interval in the square whose middle point is a set of positive Lebesgue measure. So it's not enough that on each segment we have just countable number of bad points. So what can be done? So let's see the picture. So we have a bunch of transport lines. We know that they don't intersect each other, because if they intersect, we claim which violates the differentiability. They can intersect only at the end, not in the middle, because in the middle they're all differentiable. If they intersect, then there are two gradients at a point, which is impossible. And suppose, and we know that on each of this line, there are at most countably many bad points. So suppose we can take a piece of the domain which transverse a bunch of this rays. Well, naively we say, well, we can integrate. We can disintegrate the space. Look for say variable x here and variable t here along the line. And when we integrate on each fiber, the measure, the one-dimensional measure is 0 because of the bed set, because it's only countable. So the integral of 0 is 0, right? But in order to do it, we have to somehow to rectify it, because so what we are saying is this: define this function f. So take this. Take a piece of the space, call it x, it's a minus one-dimensional piece of the space, which transverse a bunch of lines, and define the mapping for x on the base space plus T gradient of fx. Gradient of u at x, call it fx, t. And then on the space xt, so in this way we rectified all these curves. They now look something like this. And on this we can apply Fubini. So we integrate on this coordinate x and t, and the measure of the bed set in this coordinate is 0 because of Fubini, right? The measure on each fiber is 0 and the integral is 0. But how do we know that when we transport it back to the original variable, this is still 0? We have to have some measurability condition. So to justify this, we prove that this can be justified if we knew that the gradient of u itself has some Lifshitz property. If this is true, then we can rectify it and show that the measure of the bed set is smaller than some constant time the measure of its origin in the parameterized space x and t. So it's enough to show that u is countably Lifshitz. What is countably Lifshitz means that we can break the space into countable family of sets which cover the band measure such that on each of the sets, U is Lifshitz. So of course the Lifshitz constant is not, it may change from set to set and it's not Lifshitz globally, but this is enough to show that U is countably Lifshitz. So that's what so here's what we do. It will be countably Lifshitz if we can replace this distance by which is by a lambda n concave family of costs. What is lambda n concave? Lambda n concave means that the function is lambda concave or lambda convex if f plus lambda over 2 x squared is convex for some lambda or concave or some lambda which may be positive, negative. And so this is convex or concave only up to some multiple quadratic of a function we were given constant. So let's choose those En. We define En like this. Take all point on the transport lines such that there exists some point Z for which this inequality holds, provided x minus z bigger than 1 over n. It means that we take all points on the transport line such that there is a point on the line outside a ball of radius 1 over n. So we can, if the line is too shorter than 1 over n, this will not be in the set. But if the line is bigger than 1 over n, then we can take all the points which are bounded away from the endpoints by 1 over n. This will be the set. So for each point of this set, we can replace U by this expression because we know that U is the infimum over all y of x minus y plus uy. But if there is a point for which this inequality holds, we can restrict the infimum to all points which are at least distance 1 over n from y. That's why from the definition of this set will give us the same function. So we define a new cost Cn, which is a imitation of the absolute value. It's equal to absolute value for x bigger than 1 over n, and it is C2 twice differentiable and bigger or equal than x otherwise. So this is something like this. This is the absolute value of x, and we take something like this. Okay. So this is a C2 function. The second derivative can be very large because of if n is very large, because we go from derivative plus 1 to minus 1 in a very short interval, but still bounded. So this will be Cn, and it's strictly convex. So we know that U is the infimum of over all y of x minus y plus uy. Of course, it's smaller or equal to the infimum if you replace x minus y by Cn, because Cn is bigger than x minus y. That's what That's what we construct. It's bigger. And then, but if we restrict the infimum to a smaller set, of course, we get something bigger. So we restrict it to x minus y bigger or equal to 1 over n, which we assume this is just ux. So what we have is that u is equal to un, which is the Cn concave functions, the Cn concave function with respect to this quadratic cost. So now Cn is lambda convex. It's also lambda concave if you take lambda n, the supremum of the second derivative of Cn, because we can take this function, reduce from its this square function with this coefficient and get something concave. So un are also lambda concave because they are infimum of lambda concave function, and infimum of lambda concave function is lambda concave. Why un is lambda concave? Because if you add this quadratic cost here, and we write its definition here, we can open the brackets and write it like this, and you see this is a linear function. This is it's a function of x. This is a linear function, and this is a lambda concave function in x. So it's infimum of function of lambda convex in x. It's lambda concave. So what do we use here? The Alexandrov theorem tells us that a convex or concave function, or it's a lambda convex and lambda concave, has a local Lifshitz gradient. That's Alexandrov theorem. That's what we use now. And we are done. So we can filter out all the bad points where they are bag measure 0, and we prove it, we get a corollary that if mu is absolutely continuous with Lebesgue, so all these points which are null with respect to Lebesgue and also null with respect to mu, there is a map which minimizes the secondary problem. The secondary problem that we defined before, which is in particular an optimal transport for the W1, and it's concentrate on monotone map on each on the transport race. Okay, we can also prove uniqueness that this map is independent on the support of the transport plane, but we skip this because this is a little bit too technical. So I want now to go to this problem, which is called Beckman problem, which is another perspective of the W1. So what is the Beckman problem? And what does it have to do with what we did now? Take this function, given two measures mu and nu. We look for all measure-valued vector fields. So W is a vector of measures, d measures in dimension d. Each component is a measure. It doesn't have to be positive. And the divergence of W is mu minus nu. So this is what is the mean the divergence? Big formulation. So the divergence of W is this measure if for any function C infinity in the closure of the domain omega, we have this inequality. This equality. In particular, it means that if it so happens that W is smooth, then it also this is a vector which is classical with a classical divergence 0, And also, it has zero, it is zero on the boundary. The direction of the boundary is it's parallel to the boundary. Yeah. Doesn't penetrate the boundary of omega. So here is a formal explanation why it is related to the W1 problem, L1 problem. Yeah. So we look at this definition, we see that the supremum of the gradient field W plus phi by definition is zero if it satisfies this condition, and zero and infinity otherwise, because if it is not, we can always, if it's not zero for some phi, then we take this phi and multiply it by a huge number and we get any number we want. So we can write B, the infimum of this, as the infimum of all W. That's what we want, right? The infimum of all W without any constraint, plus the supremum over phi of this functional, which is, like we said, either zero or infinity. So obviously, the infimum will not be obtained where this value is infinity. Now, we formally switch the inf and the sup. We have inf and sup here. So we don't justify it now, but that's informally switch it, and we get sup and then inf. But if you look what is the infimum of W plus the grad field of W, right? This is just zero if the gradient of phi is smaller or equal to 1 and minus infinity otherwise, right? This is the vector that we multiply W. If its modulus is bigger, it's not is bigger than 1, then this infimum is minus infinity. Yeah, and so this is just a supremum of all Lifshitz function, one Lifshitz function on the integral of phi mu minus nu, which is the dual formulation of the W1. So, so we can obtain W1 by minimizing the backpoint problem. For example, if we take in one-dimensional case, we take the unit interval, what is the divergence, and we have a W, what is the divergence of W? Just a derivative of W. If it is mu minus nu, then W is just the difference between the two accumulation functions. Right? We integrate mu, we get the accumulation function. So, so the integral of W, absolute value of W, is just the absolute value of the difference of the accumulation function, and we already calculated it to be W1 on the line. Now I say a few words about another to understand, to appreciate the meaning of this minimizer W. Let me give you another formulation of a traffic plane. So we may look at the problem as a measure on a set of paths on the space. So consider the set of paths of functions in L1, or derivative is in L1 into space. So we think about it as paths and as orbits, and we look for all these which are absolutely continuous. So the derivative is in L1, and so actually it means that they have a finite length. And for each, and given a measure on a probability measure on the space, it's induced two measures. One measure which we call the traffic intensity, IQ. So how it's defined, the integral of IQ against a function phi on the domain omega. We translate it to the integral with respect to the measure Q on the set of paths, and the function we integrate is this. This is called the field length of W. If phi is 1, that's just the length of W. If phi is not 1, this is this integral. Yeah, that's the length weighted by phi. So this gives us a linear functional of phi on the set of continuous function, and this is a measure. So we can define also a traffic flow, which is a vector valued measure W associated with this Q. So it's defined like this. We take a test vector field, and in order to define what is W of Q, we test it against smooth vector fields or continuous vector field, and very similar definition. But now instead of taking phi times the absolute velocity of W, we take the inner product of zeta of the vector field with the velocity. So it's kind of obvious that we have this inequality. This absolute value of W is just the sum of the measures, the sum of the positive part of the measures. So remember, W is in general a vector of measures. So not necessarily positive, but this is the sum of the positive of the total variation of the measures, which is sum of positive measures. And we always have this inequality. Why inequality? Because the measure IQ, the traffic intensity, count all motion. Also, if you go back and forth, it's counted without distinguishing which direction you go. Like if you measure the traffic on the road, you will count the number of cars which go along the road in both ways. But the traffic flow only counts the net number of cars. Those who, if you have cars going this way and then another car going the other way, they cancel each other. So then this is why the traffic flow is always smaller or equal than this. And of course, in an optimal situation, when you minimize the cost, you expect the quality, because you don't. It will not give you an optimal solution if along a path or transport line you will go both ways. This will be just a waste of way, right? The thing is that this W that I just described is related, is actually this W that we studied in the background problem. Okay, if we formulate the transport problem on the set of paths, it turns out that the optimal measure is supported on a straight line, and the transport measure is the one which minimizes this functional. So this is just counting the number of cars the interest in the advantage of the Beckman problem is that it is really gives us a way to consider different models. For example, models of congestion transport. When in general, the optimal transport doesn't care. In the optimal transport, we don't care about what happened near us. We just care for the goods of the whole society. We want the whole transport to be as cheap as possible. We don't see what happened with our neighbors. In a congested transport, we want to avoid crowded places. So if you see that this road is very busy, we try to find another way. So if you replace the Beckman problem with some integral, or instead of integral of the absolute value of W by the integral of some function, some monotone function, some superlinear function, on the set of divergence W. This one will be considered as a model for congested transport. And for example, if F is a square, so the infimum of the square of W on this set is a very nice problem. In fact, it turns out that this infimum is solvable by a Poisson problem. W will be the gradient of some function psi. The psi is the solution of the Laplacian, of the Poisson problem. So this will be the solution in this case. So as a mathematician, we are very happy because we solve a convex problem. If this function is superlinear and also convex, this is mathematically very attractive because we know there's only one solution, and we are happy. However, so this is the case where we dislike our neighbor. We don't want too many of them too close. So the other a case when we like our neighbor. So this leads to a problem which is much more difficult because it's not convex. And I will now move to this to describe this. I will jump to this and give you another way to consider the W1 problem. Another way to consider the W1 problem and the minimum of the Beckman problem. So in this paper, back in 2011, I looked for this expression, which we saw actually in one-dimensional case, but this is in general dimension in RD. So we have a measure and mu and two measure n plus n minus, and we want to consider the infimum of this over epsilon in the limit epsilon goes to 0. Mu is a probability measure, and nu plus nu minus are those two measures which are of the same mass. So we call this M0, the measure which has total mass 0. So there I proved that this limit exists, at least for a dense set of measures in the weak star topology, and always exists in the sense of gamma convergence. I don't know if there is a proof. I didn't see a proof yet for point-wise limit, but we know that there always exists mu for which this limit is non-zero, if nu itself is not zero, and finite. In fact, in the same paper, I proved that if you take the minimum of mu of this expression on the set of probability measure, what we get is just W1. So we can interpret the Wasserstein-1 metric as the infimum linearization in one sense of the WP. This is kind of a linearization of the WP with respect to the minimal measure mu. So if we look for fixed epsilon and look for the minimum of the minimizer of mu, we know that this is a convex problem. WP or WP to the power P at least is a convex in the measure mu. So there is expected unique minimizer. So if for each epsilon we get a mu minimizer mu epsilon, and they converge to a uniform measure of the transport rays, which correspond to the W1 case. And this is also related up to some constant multiple. The limit of the minimizer here is just the optimal W in the Beckman problem. Yeah, up to a constant, because the absolute value of W is not a probability measure. It's not normalized, but after normalization constant, this is the minimizer mu. In general, the limit of this may not exist for fixed mu, because it can be infinity. And in this paper, in Analysis Poincaré in 2016, I consider this limit for a Q in the interval between 1 to 1 from 1 over P to 1, and show that there always exists an exponent Q in this interval for which this has a finite limit. So the opposite extreme. Okay, so we also know that in the case that this limit exists, this limit always exists because we take the minimum of all mu and it's finite. But we know that this concentrates, like I said, uniformly on the transport rays, and this is the measure. The measure is called the W, the flux measure. But if, for example, mu is a discrete measure, which is supported on a finite number of points, then of course the limit will be infinite if we divide by epsilon, but it will be finite if we divide by epsilon over 1 over P, because you see, if we, WP, if we raise it to the power P, it gives you the distance you shift this measure to this measure, and the gap between two points is of order, is finite, so we have to normalize it by epsilon to minus 1 over P in order to get a finite limit. But so back in 2011, in the discrete continuous dynamical system paper, journal, I considered the minimization of this not on the set of probability measure, but the set of all measures which has n support points, supported on n points. Set of non-negative measures without any constraint on total mass, which are supported on n points. So this will be, this is the limit. I call it GPN, and the surprising fact is the GPN has a very interesting interpretation. If you take this limit, n goes to infinity, we get this functional G, which is the minimum of the so-called Gilbert problem, which I will describe now the time that I that I have now. So the Gilbert problem is dependent on some parameter sigma, which is between 0 and 1, and it will be 1 over p. So let me describe what is the Gilbert problem and what is the branching transport. So the idea is that we are given some source, so let's say discrete measures which are supported on finite set of numbers, finite set of points. A source n plus and target n minus that's supported on a finite set of points, and we consider this, a graph with vertices v and edges e. The set of the vertices of the graph contains the support of n plus and n minus. And on this graph, we assign a pair of, we define the function w on the edges. So this is w is a function on the edges, which is non-negative. It represents the flux on each edge. So think about n plus as the rate of the source of some material or whatever that goes from the point in the source, and then minus the flux that go inside the target. And on each edge, we have flux, which is compatible with this. What does it mean compatible with this? It means that we have this condition that the divergence of the W is not nu plus minus nu minus. What does it mean of the divergence of W on the graph? Divergence on the graph is defined as a function from which from the edges to the vertices. So if W is a function which is defined on the edges of the graph, the divergence of W on a given vertex is just the sum of all values of W in the incoming edges to this attached to the graph minus the sum of the W for the outcoming edges. So well, I meant, of course, that W is the graph is a directed graph. So for each edge, we assign a direction also. So we have E plus and E minus V. This is the outgoing and ingoing edges. So this is just a geometric picture of a graph. So what we want to minimize is for each given a graph and given a value function on W such that divergence of W equal to the given n, which is n plus minus n minus, minimize this. So we minimize L of E is the length of the edge E, and W e to the power sigma is the flux that goes through this segment to the power sigma, where sigma is number between 0 and 1. So what is the idea here? This is sublinear. So the cost of transporting two parcels, for example, W1 and W2, separately is bigger than transporting them together. We have this. So therefore, the transport prefer to is looking for a more densely populated area, and we minimize with respect to W on a graph and with respect to all possible graphs. So this is a problem. It's a terrible problem. We should look for all graphs on the domain in our N, for example, which minimize in all function W, on all fluxes W on the edges of the graph, which satisfy this condition. By the way, notice that this condition means that for each vertex which is doesn't belong to the support of nu plus nu minus, the net it gives you zero. The net the incoming minus the outcoming flux is zero. And if you are in a source, then you get positive. The outcoming minus the incoming is no plus, and also for the target. So this is sometimes called the Kirchhoff condition for flux on the graph. So this is problem is defined for general embedded graph. However, it is known that the minimizer is always on a tree, on a graph without cycles. So this is kind of intuitively reasonable because you don't get anything from closed loops. So tree is a graph without closed loops. So we can, so there is this version of the Gilbert, which is called Gilbert mailing problem. In the mailing problem, we are given a transport plane. So in general, so we know which address we should go. We know how much mass or whatever we should move from vertex V to vertex V prime. Yeah. This is like the set on which we define the transport plane. But now we fix it. So we view this as a flux of mass from V in the source to V prime in the target. So in this sketch, you can see, so for example, I didn't send the arrows, but suppose these are two sources, and we go this way, and then so we know how much this send here and how much this send here, and so on. So usually in the literature, we define this as like described before on a sigma algebra of Lifshitz path, and we use using Lagrangian description. But I want to give another description, which will be very close, actually, to the honest-to-God optimal transport, to the optimal transport as we know it. So, so let's define this for each pair of vertices on a graph, on a given graph. We define this function which has a source at a point V, the prescribed point V, and the targeted point V prime. So this is a flux on the edges, and okay, so this on each orbit connecting, we denote the orbit of edges connecting vertex V to vertex V prime by this, or V prime, and the set of all functions which satisfy this equation is if this is a tree, then it contains only a single flow, which is 0 on the which is 1 on the path connecting V to V prime, and 0 otherwise, right? Because it has to it should take the flux of intensity 1 from V to V prime, and all the flux going through a single orbit. So it's either 1 or 0. In general, the Gilbert mailing problem can be described now in this way. Instead of writing sum of LE times WE to the power sigma, I describe to you here what is WE explicitly in the case of the mailing. The WE is the collection of all a transport going through the plane from V to V prime. We sum over all sources and all targets through which go through the edge E, and we collect all them together and put them in the power of sigma. So, okay. So we can write it like this, okay? Like I said, the W pi is just this sum, you know, that's what it is. The convex relaxation of the Gilbert-Pellic problem is this. This is the same, except that now I put the power 1 over sigma here. This is exactly the same. It turns out that this is a convex problem. And the convex problem, moreover, it can be extended to a convex problem on the set of probability measure on the whole space. And if it turns out that this measure is supported on a tree, then it is precisely this one. Why? Because on a tree, all W are either 0 or 1. So we can take the power of 1 over sigma, it will not change it, right? It will be the same. So the limit problem that I described before give you this functional over all graphs. Here we minimize over all measures which are supported on endpoints and take the number of points to infinity. This is not so good from numerical point of view because it's not a convex problem, right? Even though we can fix n and minimize over finite dimensional, we minimize the problem not on the whole measures in the world, but on the finite number of variables. But it's very bad because it's not convex. It may have many minimizers. But if I use the minimum with respect to the all probability measure, then I can define this distance, right? And I can define this distance for a measure mu and define a distance which depends on the measure mu. It's a convex function of mu. And then I claim that if I take this functional, sum over all minimize this function with respect to mu. This is now fixed. Minimize this with respect to mu. This is a convex problem, and the minimum will be if the minimum is, in general, the minimum will be supported on a graph, finite graph. This is a thing that it looks very reasonable, but still I don't know how to prove it. But if it is minimized on a graph which is a tree, then it is the same, precisely the same. So this will give you the solution of the Gilbert problem, which is highly non-convex. So this is just, in this way, this is a convexification of the Gilbert problem. So this is what I claim, the Gilbert problem corresponding to sigma equal 1 over p, when p is the Wasserstein distance that we used to define this is the Wasserstein distance which we use to define this function. Okay, I think that that's more or less what I wanted to show you. The rest is just the derivation of this result, which is not, this is too technical and too late. So if you are interested, I can send you some reference. It's not published yet, but it's in the archive. One of my recent paper in the archive, which you can see this derivation. And thank you very much for the moment.
Questions?
Yeah. If this is a concave function, if this is a concave, I'm not sure this is could be, but in this case, you don't expect uniqueness. I think there should be, but I'm not sure that this gives you all the solution, because then there may be some solutions which are not smooth, and they are not. They cannot. You cannot obtain them from the variational from the Euler-Lagrange equation. Yeah, maybe in the concave case, I suspect.
Any other questions? No. Okay, so then let's thank Professor Wolansky for.
Thank you very much.
Okay, so thank you, and thank you for coming. And